Remember the example that I was planning on doing that I didn't quite get it right? It was my non-recognition of what was going on. It is in fact correct. And I'm glad that I was discussing this subtlety because it comes in handy when we study the Dirac delta function. Turns out the delta function is not a function at all. But nonetheless, it's very important. So the example is square root of x plus y. What I'm trying to show you is that while indeed partial derivatives may commute, you can take partial derivatives in any order, there are some restrictions to it. Namely, I mentioned both the partial derivatives should exist, one of the double partial should exist, and it should be continuous, right? That's the exact concern. So let me do this. Let me do df dx. I don't have to worry about y. This becomes that. Let me do df dy. That's just 1, and that's about as nice as a function can get. So I can take the double derivative, or rather the x derivative now, and I get 0. Now, the whole problem exists when x is equal to 0. When x is equal to 0, this function is not defined. Huh? 1 over 0.
Yeah.
Therefore, I don't care what it is not defined when x equals 0. In fact, this is defined everywhere else when x is not equal to 0, and it's in fact equal to 0, and it's equal to this. But just at that point x equals 0, this guy is not defined. Yep.
Are you using a 2 over there?
Yep. Thank you. Good, good. So we might hastily write, so look, when x is not equal to 0, this is also equal to 0. But it doesn't make sense to define the y derivative at x equals 0, because at x equals 0, this function is not defined. On the other hand, here it is, and that's the distinction. Yeah? Okay. So it's a little catch, and the catch invariably is when the function is not defined. We will have another integral that looks very nice, or another divergence, a derivative, that looks very nice, except at one point where it's infinite. So we cannot pretend that, oh, it's true everywhere else, but at one point we can ignore that point. We can't. That creates the Dirac delta function. Okay? Is that clear? Sounds like a technicality. We don't have to dwell on it. It's not really what we do, but I'd like to present objections. When you take derivatives, be careful. The function has to be defined. The function is not defined, well, if algebraically the derivative works out, it's not true at the point where the function is not defined. Okay, moving on. I would like to, so we talked about this. Again, I tend to move rather rapidly, and I'm just talking and talking and talking, but it falls upon you to raise your hand and ask questions, okay? If there are any questions at any time, in class or outside of class. We talked about delta t, and we can sort of write this as dt ds when t is so t is a function of x, y, and z, and x, y, and z is a function of some variable, S. And then we have seen that this can be written as gradient of t dot dl ds ds. We have seen that already. One of the things I'll be doing today is showing this by an explicit problem. This is rather abstract, but and a short form of this, writing this, is yeah. So I'd like to illustrate this, and you know what is this? I want to clarify. By dl, I mean dx x hat plus dy y hat plus dz z hat. This is useful when we're doing a nice simple integration along one of the coordinate axes. Sometimes you'll have to do integration with respect to s, and I'll clarify both. In that case, what will you do? You will write this as and that way you can integrate. Okay? So the basic thing that we have to learn, and this is what I will do, is, and these are called line integrals. They're not called line integrals because we're integrating over a line. They're called line integrals because we're integrating over a curve. And the curve has what's called a line element. Okay? So a curve is sort of a generalized line, right? So you have some curve in space, and you're going from A to B. And this is the quantity that you want to integrate, but this is some quantity, some vector. Gradient of t is a vector. It doesn't have to be gradient. For this formula, it has to be gradient of t. And I'll recap this example with the same formula. But first we want to learn how to integrate any vector along a line integral. So what I'm trying to do is define this guy, A to B, some vector dot dl. Okay? Through this path. So what is dl and what does the picture look like? Well, the picture looks like this. At any point, the line element, dl, is tangent to the curve. A vector v, in general, is not. It can be. So let me show you what this is v, huh? And v can look all sorts of interesting way. See, it can change length, change directions along the entire curve. But we want to integrate this. Physically, what does that mean? I'm dotting this with that. So I'll take the component of v in the direction of dl and make the dl small enough and then add it up. Correct? This is what I mean by a line integral. We have to learn how we will actually do this line integral. Okay, it's nice to sort of write it out, but how do we actually do the problem? Before we do the problem, is this clear, the diagram? You're taking the component of v at every point along the line, small line dl, small infinitesimal line element, and then you're adding it up, adding it up, adding it up, in the limit that dl goes to 0. Remember the old formula for Riemann integral, although we don't think of it as these sort of Riemann integrals, but that is the underlying philosophy. So let's pick a vector field. I could pick any vector field, but to illustrate, I'm going to force the vector field to be the gradient of a scalar. I don't have to, but I'm going to. And I've written it out so that I don't make a mistake. It is, so this is a sort of a long example that we do slowly. Example, consider a function f. I'm going to make this two-dimensional because at the end of the day, that's all I know how to draw. 2x squared plus xy. And I'm going to integrate this till I'm done with integration. That's example. But this is a function. That is not what we're discussing. We're trying to integrate a vector field. So define a vector field so that I can illustrate other properties as well. Define V to be equal to gradient of f. Again, this doesn't have to be the case. I just picked that as an example so I can illustrate other features. Well, what does that mean? Melissa, I'm going to put you to task. I know this is your first day here. Give me the x component of gradient of f. I want to make sure this is the function I picked. Yes, it is. X component of the gradient of f. Speak up. It's okay to be wrong. You don't even have to win. You decided that. Okay, your excuse for today, but by Wednesday you should be on it. Yeah? I'm going to go this way. Martin, what's the x component of the gradient of f?
4x plus y.
Correct. 4x plus y x hat. What I'm doing is taking the partial derivative with respect to x. Obviously, this one will have a y component. Ashik, what's the y component? X, y hat.
Yeah, y hat.
Yeah. No, I said, what's a y component? The y component is x. The vector itself is y hat. There's no z component, so there's no z component to this vector. Fine, I have a vector field. Now I have to decide on a path. So again, I'll decide, the more complicated the path, the more complex the integral. So I want to pick a simple path to illustrate the point, but I also want to pick a slightly more complicated path to see that we are able to do it in principle. Then I'll just pick a maniacally bad path and then cheat. So the path I'm going to choose is the following. X, Y. I tend to zone off after a few minutes and not pay attention. So if I make a mistake, please catch me on this one, okay? So this is the point 0, 0. I'm going to call this the point A. This is the point 1, 0. I'm going to call this the point B, and 1, 1. This is the point 1, 1. I'm going to call this point C. And the first path that I'm going to choose is going to be I'm going to go this way and that way, and I'm going to call it path 1. So I will write this abstractly as V dot dl along path 1. Yeah? Good. So what I'm going to do is break this path 1 up into two obvious smaller paths. I'm going to go from here to here and from here to here. Okay? So, along this path, dl is what? Just dx. That's why I'm doing this, to make an easy path. Over here, dl is what? Okay? So now I'm going to do, I know it's the first example, but because this is an upper level course, even the first example, I'm going to drop some simple steps. Tell me this dot dx, x hat, what is it going to be? Well, what is v dot dl along this path? So pay attention, everyone.
Or it's just taking a dot product, right?
Correct. Take it correctly.
Y component goes away.
Correct.
And what's left is 4x dx plus, or 4x plus y times dx.
Correct.
I just put it inside.
Correct. Now I'll put the limits. First of all, is this clear? I've just taken the x component. Now I have to set limits and other things. Along this entire path, what is the value of y? 0. And then x is going from what?
0 to 1.
Yeah. Okay? Plus, now, the other path. What do I do?
Do that from B to C, right?
From B to C.
You do the 3 dot D y n.
Okay, so now tell me what goes in Chip. X dy. What's the value of x along this entire path? 1, right? So this guy is just 1. And y is going from where to where? 0 to 1. Can you integrate this? This is what? 4x squared over 2, right? Please, is that correct? This is where I lose myself. I zone off. 0 to 1 plus, oops, y, 0 to 1. 2 plus 1 is 3. Check. Ask questions. I want to make sure I got 3, and I did. X squared, when it's 0, it's 0. When it's 1, it's 4 times 1/2. Or 2. Integral of dy is y. If you put limits 0 to 1, it's 1 minus 0. So it's 1. 2 plus 1 equals 3. Yeah, I want to, the basic reason is I want to hang on to that picture. And I'm going to redraw for the sake of the video. Now what I want to do is go from A to C. So I need DL. picture that I'm going to draw, dl looks like this. What I'm going to do is do it slightly the long way, but it becomes very easy because this will always apply. I'm going to parameterize this curve with S. It's a straight line whose slope is, it's going from 0, 0 to 1, 1. What is rise over run? 1. So is this given by, it is some x of s along this curve and y of s. Will this work? Is that a good parameterization for that curve?
I mean, it looks like the 1, 1, 2, 2, 3, 3 line.
It's 1, 1, 2, 2, 3, 3 line. Well, I'm going to make sure that I put you to task slightly. What if I'm doing this curve? This is 1, 2. And this is x of s, y of s. In this case, how would you parameterize this line? What is the slope of this curve? 2. 2 over 1. 2. How would I? For every 1 meter that I go, I have to travel, 2s. Yeah, that's how you would parameterize that line. But that's not the line we're doing. We're doing this line. Yeah? So, in principle, you could parameterize all lines. We've seen how to parameterize a parabola, s squared. So, you have to be clever about it. And again, this is not a math course, so we won't have exceedingly difficult parameterizations. It'll be always reasonable. You can sort of think it through. And if it's an exam, you can work with me and we'll come to an answer. Okay, so let me, the reason I did this, excuse me, is I need my DL. So I'm going to write DL to be equal to dx x hat plus dy y hat, and dx just turns out to be very simple here. It's just ds. Yeah? Too bad this is, again, a straight line. If this were a parabola, I would get 2s ds. Okay? So then, and I'm going to call this path 2. I'm going to do the same thing. 4x plus 1 ds plus xy ds. I'm not putting in the limits yet. I'm just going to put it as path 2. We'll put in the limits shortly. And now you're looking at this going, this is kind of nonsense. I don't know what this even means. But do you see that all I've done is just the, where's my 4x plus, y e plus 4x plus y. Yep. So these are actually two integrals. Is that clear? I just took the dot product. Okay? Now, I don't need to see x and y because I don't know how to do ds, but that's okay. Again, this happened to be just a very comfortable line. So then I would do 4s plus s ds plus s ds. Oh my goodness, what is that? 4s, 5s, 6s. Correct? What do you find? This doesn't have to be the case. But in this example, by design, it has to be the case. First of all, let's discuss why it doesn't have to be and why it is, in fact, the same here. Before we do that, any questions with the math?
Why do you end up picking 0 and 1 as our bounds?
Oh, for the limits you mean? Yeah, so as I go from here to here, s is going from 0 to 1. Good question. Now, why? Huh.
No, I'm just looking at it from the help.
Yeah. So again, let me categorically state that it doesn't necessarily have to be the same for all problems. In this case, I didn't choose any vector field V. I chose a very particular vector field V. So it would appear that V dot dl equals 3 along both paths. Yeah? So, and the question is, why? Well, here's why. In this problem, it was gradient of f dot dl. Yeah? And gradient of f dot dl is nothing more than df, so df from A to C. Correct? Along both paths. It starts at A, ends at C. Well, we know what that is. It has to be f, so f evaluated at C minus f evaluated at A. Well, let's do that. What is f evaluated at C? That means I put 1, 1. It's 2 plus 1. Voila. And f evaluated at A is 0. Therefore, delta f, which is actually equal to this, is equal to 3. Is that clear, guys?
Oh, I kind of got a question.
Yeah.
Here. So from 4x plus y ds, from there we went to the s, right? All the parameters were
Yeah.
s. That's because
That's
the
because of that particular line.
condition in the circle, right? Now that
Correct.
if that was a line of slope 2 and s is it's s and 2s,
Yeah.
it would have corresponding changes here too, right?
So I'm going to erase it, so let me write it in a different color. It'll be 2 here, it'll be 2 here.
Right. Thank you.
Yeah, or let's say it's a parabola, I would get this, then this would be a 2s, again 2, because the derivative happens to be 2. The derivative of s squared is 2s ds. 2s ds. Yeah?
Yeah, and how do you find the endpoints for a certain S again?
Yeah, so if I parameterize this guy, this curve as x of s and y of s, when is x and y 0? When s is equal to 0. When is this point 1, 1? When s is equal to 1.
What if it was like 2x instead? Or
If-
S and 2s? Then,
If it's 2s, it's whatever that value is. Then you mean to say if it's like this curve, right?
yeah. Then
Yeah.
it would be from,
Then x will still, it depends on how far s is going. S is still going only from 0 to 1. Y will go from 0 to 2. Yeah? And remember, I can pick any parameterization. I just picked s. I could make it difficult and make it s cubed. You will get the same answer. Just a mathematical parameter. It has no physical meaning. Yes.
I guess I'm confused about what makes these two the same. Like, is it something to do with it being the gradient?
It is because
Okay.
it's the gradient.
Okay.
If it were in the gradient, it won't be the same. Yeah? So let me end this example with something that I'm fond of doing in an exam. You know, I will give you this vector field, V. And I know I'm going to start at 0, 0, and 1, 1. And I will ask you to compute over this curve, like a sine function. I don't mean for you to do this over the sine function. I can guarantee you that. You could, if we had all the time and if we had developed careful techniques, you write it as a function of s, some sine s, or whatever it is, you know? You could. But what would you do? Because I know that the integral is path independent. I would pick the simplest path possible. Let me end this example by reiterating the most important feature, which is delta t, which is equal to tb minus ta, some point a and b that we start from, a to b, gradient of t dot dl. This is what delta t means. This is a formula. This is nothing more than the fundamental theorem of calculus. The integral of the derivative is nothing but the difference in the endpoints. It's the fundamental theorem of calculus in a vector case. If this is one-dimensional, this is what you would call the fundamental theorem of calculus. It is true that for any dimensional integral, there's a fundamental theorem of calculus. For a line integral, it depends on the endpoints. For an area integral, it depends on the boundary. For a volume integral, it depends on the boundary. For the fundamental theorem of calculus, for the area integral, it will be called the Stokes theorem. And the fundamental theorem of calculus, for the volume integral, will be called the divergence theorem. They're both important for us. Yeah? But very likely, I can only define the area integral today. I'll do an example the next time we meet. I'm going to make it an area. So let me call this x and y, sort of a perspective. There's a 3-dimension here, but I won't be too concerned with this in this drawing. let me start off with this nice area. I wish to integrate some vector field along this area. It's actually a flux integral along this area. So what we're doing is computing the flux. Let me explain what that means. So I'm going to pick a small chunk, and I'm going to call that chunk dA. So dA, as you can imagine, is nothing more than dx dy. Do you see that? Dx and dy. Why is that? Well, because this guy is dx, this guy is dy. But what we want to do is define area vector, I said it, area to be a vector, yeah? Or dA to be a vector. To make it a vector, I need this guy, obviously, but I need a direction. If you have to include, if you have a notion of direction of a surface, what's the best direction to pick? You have to give me one direction, huh? Normal. So, in this case, that's, again, I know it looks long, but it's a unit normal. So then my area vector is dx, dy, n hat. Okay? Problem is, there are two normal vectors. Up and down. Two normal vectors. They're called the orientations. When we do an area vector, I have to clarify which is the one I want to be the normal vector. Okay? These are called the two orientations. That depends on Stokes' theorem and divergence theorem. Now, what happens if your surface is not such a nice plane? Well, you have to use some sort of a calculus technique or different coordinate system to come up with some area. And we'll do it. But it is still possible to define a normal vector and call it dA, and then the vector itself is understood to be dA, normal. And by area integral, I mean the following. Take a vector and dot it with this, and you integrate over the area. Again, for every area, there's for every area there are two normals. Somehow, the context has to be made clear as to which normal we're talking about. It'll be made absolutely clear. There's no confusion in this at all. In particular, let me talk about the integral around a closed surface. Area integral around a closed surface. I'm not good at drawing this, but imagine a beanie bag, smooth. So this is a three-dimensional structure. The boundary of the structure, maybe even it's a ball, where the boundary would be the sphere. Okay? So this is understood to be 3D object. This is a two-dimensional boundary. So this is the 2D. When you have a closed surface, I will never tell you which normal to use. This is the normal you use, the outward normal. If you have a closed surface, one normal points into the surface and one normal points out of the surface. We actually want to compute the flux, things flowing out of a surface. That's the idea. So this will always be the case, outward normal. And in this case, when you have the area of a closed surface, it's denoted like so. Look, a circle around the integral. And you are to understand that this means outward normal. My goal next week, or sorry, Friday, is to do one of these. So as you can see, our toolbox is being built up steadily. So we'll have divergence theorem coming up here, Stokes theorem. We will learn to use 3 different coordinate systems so that we can do curved surface as well. We'll use the cylindrical coordinate system and the spherical coordinate system. If you need more complicated surfaces, well, we invent more complicated coordinate systems, at least locally, but we won't. That doesn't really interest us. Again, our point is not to do all these surface integrals. We're trying to do useful things so that we can do physics. And then we'll conclude with the delta function. And that's your toolbox. Okay, so this, depending on your experience with math, this may or may not be tough going, but remember, in my guess, in 5 more lectures, 9 lectures is typically chapter 1. All the math is completely developed. And so this is 4 lectures, we're halfway through with all the math skills we need. But remember, it's a steep curve, right? Every